This video, I'm gonna introduce you something called a difference quotient, and basically these are the baby steps into, the real fun in calculus. So I've got two examples here. I've got finding the average rate of change of some function and finding the instantaneous rate of change. Now, what should be noted is that actually finding the instantaneous rate of change is a really big idea, more, sort of bigger than finding the average rate of change. And we'll get into that. So let's say I asked you to find the average rate of change of some random function I've drawn here, right? Let's start off with labeling. So at this red dot here, I'll call this x, and at this other red dot, I'll call this x plus h. And the reason I did this is, well, it's basic if you think about it, right? The distance between this and this point, there is some distance, right? So I'm expressing it like that. So there's a distance h. I'm calling this random distance, I don't know. So, distance. And I'm representing it by a variable. So it's basically this x value plus that distance gives me, the x point here. Now, the whole point of it, like the way an average rate of change is calculated, is all you do is you basically find 2 points, and then you basically just draw a line through them. That's the average rate of change. Or in other words, you're finding the secant, right? Because that's the average rate of change, the secant. So if I continue my labeling here, if I plug x into the specific function, my output would be f of x, right? Whatever this function is, we don't know. We're just, describing it in, like, generally speaking. Now, if my input was f of x plus h, my output would just be f of x plus h, whatever that may be, right? Again, we don't know what it is. Whatever you put in is what you get out. That's basically it. Now, you may notice that the secant line basically looks like a linear line, and it is. It's a linear function. So what we can use is, if we want to find the average rate of change, we can just use slope formula. And if you recall correctly from grade 9, slope formula is basically m equals to y2 minus y1 over x2 minus x1. So let's sort of do the, derivation of this. So the m, and I'm going to call the secant, or you can write m average rate of change, equals to, well, y2 minus y1. Well, in this case, f of x plus h, this can become y2. F of x can become the y1. X can become x1. F of x plus h can become x2, right? And so basically now we're just using the slope formula here. So we just put it in. Oh, let's keep this in the nice yellow. F of x plus h minus f of x over, we're going to put in our x2, which is just x plus h minus x. Now, simplifying this, well, we can see that the x here in the denominator cancels out because x minus x. So we finally get f of x plus h minus f of x over h. And that's the average rate of change formula. That's basically how you do it. Now, what if I asked you to find the instantaneous rate of change? So at some point x in this graph, I asked you, find me the rate of change at that specific point. In other words, what is the tangent here? Because that's basically it, right? Because if you draw a tangent where it just touches that point and doesn't touch anything else, you're finding the instantaneous rate of change at that point. And you may have done this before in your physics classes. You may have just, your teacher, draws a nice little VT graph or whatever, some DT graph, and then asks you, all right, what's the rate of change at that point? Here's a ruler, figure it out. We're going to do this with math now, because using a ruler like that is for losers. So we're going to do it with math, with, a pencil and a paper. That's it. You don't need a ruler. So looking at this previous average rate of change, it's the same graph here, but I just labeled it. Let's say I just color this red dot as blue, just to show something to you. So let's say, and then I have the same thing here, x plus h, right? And I have this nice little blue dot. Now, what if the distance between these 2 points got so tiny that it just approached 0? what would that mean basically? Would that allow us to find the instantaneous rate of change over here? Well, yes, it would, right? If the distance between x and x plus h gets so tiny and tiny and tiny and tiny and tiny that they're basically, if I'm drawing like a little image here, that they're basically right next to each other, if not the same thing, right? Then we can sort of find the instantaneous rate of change. So this is applying what we were talking about in the last videos of something called a limit. We're going to be using limits here. So the formula for this tangent line to express the instantaneous rate of change is, well, and I'll call this tangent, or you can write instantaneous rate of change, is basically the same formula of the average rate of change. So I'm going to write a little space here, f of x plus h minus f of x over h, and add a nice little limit. The limit as h approaches 0. Because again, if the distance between x and x plus h keeps shrinking and shrinking and getting closer and closer and closer and closer to each other, eventually it'll just be 0, and x will sort of be like x plus h, right? And then so this is sort of like a hack to basically find the instantaneous rate of change. Instead of drawing tangents all the time on a graph, right, it's better to just do this, because when you draw, there's always some human error involved, right? This is as precise, as accurate as you can get. So this is the math way of finding the instantaneous rate of change. So you may ask, all right, so what? Big whoop. Why do I care? Well, you're pretty much going to be doing this in the entire course, and you're not going to be drawing tangents with a ruler, which is something you should be grateful for. But basically, when you find like the general, when you use this formula here, and you find whatever function you get. So if you don't substitute anything for x and you get rid of your h's at the end through algebraic manipulation, you eventually get something called the derivative function. Derivative function. So using this will get you the derivative function. So okay, now you may be asking, all right, you've confused me even more. And actually, I hope not. What does this mean? Basically, let me show you this example actually. Just keep in mind in the back of your head the idea of a derivative function. So we have a function here called y equals sine of x, right? And we have this function called y equals cos of x right here. If we look at, let's say, just some random point here, let's say this, and we drew a tangent line, what is the value of that tangent line? Pause the video and think about it. Okay, so the value of that tangent line is just 0, right? Because it's just a flat line like this. There's nothing really going on. Yeah, I drew this on the y sine of x. In the derivative function, the value of the tangent would be expressed in the y value, and we can see that right over here. So actually, the derivative, and just, I don't know if this will confuse you or not, but the derivative of y equals sine of x equal to y of cos of x. And if you look at this, just looking at the graphs, forget any algebra or anything else, just look at the graphs and think about this. If we drew a tangent right here, like I just did for here, and the value of this tangent was 0, then the value of this function, of that y value, was 0 as well, meaning that cos of x is the derivative of sine of x. So if I write this down, the value of the tangent is the y value of the derivative function. So think about it here, right? Again, I'm repeating what I'm saying. The tangent of this is 0, right? And this is some x point 0. Let's say that we drew a tangent right here, right? We can say, well, that sort of looks like, like y equals 1, like if it was y equals x, right? And if we look at the derivative function, we see that, well, this is 0 and 1, right? So the value of this is 1, and we can see in that y value, it's 0 and 1. So the rate of change, in other words, the rate of change is modeled in the derivative function. Let's look at another example of y equals sine of x. If we put the tangent here and we drew it, right, this sort of looks like y equals negative x, right? So that could be like, negative 1. And if we see here, well, this is 0. Sorry, not 0. This is whatever x value this is, negative 1. So this is negative 1. The rate of change is looking like negative 1 over there. Then the y value of that is just negative 1. So hopefully this sort of made sense, because, and the reason I show these trigonometric functions is because it looks a little more clear than some other functions. I could be wrong, but basically that's the idea. And if you want to think about this and try this for yourself, do this. Put f of x equals to x squared in Desmos. Try this in Desmos. So put this in Desmos. Right? And then in Desmos, again, put f prime x. So when you put this little apostrophe over the top, that's showing the derivative function, the first order derivative function. So this is read as f prime of x. Just put that in and you'll get something. And it'll show, if this is equals x squared, it'll show you, nope, it doesn't look like that. It'll show you the derivative function. Put that in and I'll give you a hint. The answer is y equals 2x. That's the derivative of y equals x squared. Think about it. And the way you'd find that is to use this. Use the tangent formula. Because the whole point of the derivative function is to model the overall rate of change, is to, not even overall, is to model the rate of change of that specific function. So I feel like you're going to be really confused. I don't think so. I've done an incredible job of explaining this. If I did, please let me know in the comments. It's just, this can be sort of tricky for some students, and for some it's like super easy. This is just how I've understood it, and I tried to display the best version I could. Let me know if this was helpful or not. If not, I'll take this down and make a new one. But basically, I tried just to show the intuition behind the idea of the derivative function. It's all about, another function modeling the rate of change of the previous function at those points. So hopefully this all made sense. If not, you have your teachers, you can say this guy sucks. But yeah, that's basically it. In the next video, I'm just going to be showing sort of algebraic ways of finding the derivative function. So I'm going to be working through 3 examples and just showing the algebra behind it of how to find a derivative function. And yeah, that's pretty much it.